by the early 20th century, people realized that mixing is also very important for balanced nutrients and diets. And uh, today, mixing technology, we can't really imagine food production, or whether food or feed production, chemicals, pharmaceuticals, cosmetics, without mixing.
Welcome to the Feed Science Podcast, coming from North Carolina State University's Prestige Department of Poultry Science and the Animal Food Manufacturing Program. My name is Adam Farnols. On behalf of Wise Genetics, thanks for joining us today and listening to our podcast. We appreciate all the support. Our guest today is Dr. Dejan Miladinovic. Dr. Miladinovic is the head of the Feed Technology Center at the Norwegian University of Life Sciences. So we are leaving the United States for today's podcast, which is always exciting. Dejan, thanks for joining us.
Thank you for inviting me. Absolutely. My pleasure.
Absolutely. If you wouldn't mind, a couple things. Give the audience a little bit of your background. I know we've had you before, but a little bit of your background. And then also, if you wouldn't mind telling us a little bit about what you guys do there at the Feed Technology Center, that would be great.
Yes, right. So, as you mentioned, my name is Dejan. I've been working and studying in the fields of agriculture. So basically, I have finished my high school first through veterinarian sciences, and then I went through zootechnique, a little bit of genetics, and further on to technology. So I've started working at the Center for Feed Technology in 2005, and then I've literally started from the ground floor, operating the machinery, and nowadays, since 2016 or 15, if I'm not mistaken, I'm a head of a Center for Feed Technology at the Norwegian University of Life Sciences. My PhD is related to process engineering, where mixing technology and all other technologies that are incorporated into the feed production are actually packed well.
And what kind of work do you guys do there at the Feed Technology Center? Is it mostly academic, or do you work with outside industry, process development, nutritional work? What are all the kind of things you guys do there?
Well, basically, Center for Feed Technology is head-to-head in a way with Department for Aquaculture and Animal Sciences, and we are also part of Animal Experimental Center. So basically, the entire package that we are having is from nutritional perspectives of developing the diets, further on to establishing new goals in a way, how to prepare maybe or how to spot potential novel ingredients or novel processes and so on, further on to doing the processing, the manufacturing, and developing the technology around this manufacturing, as well as sending this feed further on to biological experiments with aquatic organisms and also domestic animals.
All right. So I think kind of our primary topic for today that we discussed is to talk some about mixing. That's obviously work that you've done some in your academic career, and you guys are still working on there. And I think you've got some interesting things to share about some new technology in that space. But before we kind of get to that, let's just talk a little bit about how mixing actually works. I think in a lot of cases in the feed side, we have our mixer. At some point, that mixer was validated, and it said, "Hey, if I put everything in here and I turn it on for this amount of time, I'll have a nice uniform mix." But there's actually a lot more complexity that goes into that based on particle size and shape and density and friction and the amount of liquids and things like that. So how in your guys' experience and in your academic work, can you tell the audience a little bit about how do things like shape and density actually influence particles moving inside of a mixer?
Yes. Well, in order to explain how the things function, then I need to really start with the story. When I was invited after a conference, feed manufacturing conference, I was invited among 12 professionals within this field to the meeting where we discussed about potentially new book, feed manufacturing book, because there was a very nice book that was published a long time ago by American Feed Millers Association, but somehow that book wasn't updated, and we were discussing about the book. So I was invited to write about mixing process. And of course, when you are talking about mixing, when you're talking about anything, you have to start from the beginning. And this beginning, basically, it's a story of powder mixing and a history, evolution of powder mixing that has been for thousands, actually, of years. According to some scarce literature, it all began over 40,000 years ago when there was this creation of these ancient medicines. And then around 700 years BC, the Chinese invented the gunpowder, and then that required really very precise and careful mixing. And it was, of course, valued for very specific reasons, so that something wrong won't happen, because it was happening. So mixing of feed and mixing of food came, of course, much later. And one of the earliest examples of this mixing is making food, making pastries, basically. I don't think that early humans did consider mixing for better taste or better nutrition. But then evidence shows that actually people began really mixing food ingredients for about 30,000 years ago. And that, guess what? That was related to baby food, which is really like impressive. And that was actually found just recently by some research group at the University of Novi Sad in Serbia, that early humans they mixed also, of course, except the baby food, they mixed different colors for cave paintings and so on and so on. But for a really long time, there were no major advances in mixing technology until somewhere in the late 19th century. Of course, that period was the period when there was this burst of innovation, where, of course, mixing methods needed to be modernized in order to create certain products. But then, by the early 20th century, people realized that mixing is also very important for balanced nutrients and diets. And today, mixing technology, we can't really imagine food production, or whether food or feed production, chemicals, pharmaceuticals, cosmetics, without mixing. Of course, mixing technology combines different techniques to meet all these specific needs for the specific industry. But for us, for feed millers and feed technologists, mixing came as a very important step-by-step guideline for performance of certain products. And then when we are looking at mixing technology, of course, we are looking at mixing factors. So there are several mixing factors that we always need to include in order to really mix certain ingredients, whether they are novel or commercially available. And first thing that we think of are or is size of particles, because you need to specify an optimal size for these particles to be mixed together, especially if you have many different ingredients, as we are having nowadays in a feed diets. Look, before just 40 years ago, in the 80s, fish feed was just like 3 4 ingredients. You had a little bit of starch or I don't know, wheat flour. You had lots of fish meal, and you had some fat, some oils. But now it's different. Now you have 40 different ingredients, and you're changing the diet or formulation on a maybe weekly basis. Some companies even on daily basis. For these kind of things, you have to understand not only the size of a particle, but you have also to understand the shape of a particle, so the geometry of particle. You have to understand the density of particles, because higher density between the particles should be large difference between the densities should be avoided, because you want to avoid segregation as much as possible. And then if you have, let me say, some active ingredients that you want to add, then you have to think of concentration of these active ingredients, so that you will uh, avoid certain concentration of some materials that could be even toxic. And good example could be selenium. So if you have 0.01% of selenium in the diet, that's really very good in a way, with a huge potential for biological experiments with the animals. But if you have this 0.01 that you have added segregated, that is actually behaving as a poison later on. So you can kill an animal. It's mixing. So mixing technology is that important. So that's the stage of mixing technology that could help you understanding that interaction between particles will be optimized. Aggregation will not happen. This caking. How do we say that typically? Um, and then when you understand the interaction between particles, concentration, density, shape, and so on, then you can just say like, aha, okay, right. I will need to have this kind of mixer, that whether that will be twin shaft pedal mixer, or it would be other types of a mixer. Uh, so once you know what kind of mixer do you want to have, of course, the mixer choice is one thing, but considering that feed production is really extremely actually dynamic process, then you need to look at the mixing time. Each diet that is sorry, each diet that is containing ingredients which is maybe prone to segregation must be examined before you will even include it into the diet. And that's what I'm always stressing. This is really very important, because feed technologies, and nutritionists, I have feeling after this 20 years of my experience, they don't really communicate very well.
Well, yeah,
Like they don't
yeah,
speak the same language, you know.
abs-
Yeah, and that's why I'm saying, like, when they start communicating, then they lose kind of step within this decision. In the end, they start communicating about certain things that they on both sides are not really prepared to discuss. And that's why I'm always saying, like, it's very important that you discuss on the even daily basis, so that you learn each other's language.
hmm So yeah, I mean, I think some of those things that are really important, and it's difficult, and this is true for a lot of what we do in feed manufacturing. It's in many cases there is either no one right answer, or just the amount of data that exists and the amount of different interactions that exist make it a very large big data problem to determine what's perfect, because we know that We would love to have all of the particles that are going into the mixer that need to be mixed to be the exact same size, exact same shape, exact same density. We'll get a good mixture of everything, but that's not reality. We might want to use a coarser grind cereal grain for broilers so that we get proper gizzard development. We might want to use a finer grind cereal grain for swine for the purpose of more efficient energy utilization. Some of our trace minerals are going to be very, very small. Some of our synthetic amino acids are going to be pearled and be larger. Some things are more round. Some things are more cubic. If it's round, it moves through the formula, it moves through the mixer better. If it's cubic, it doesn't move through the mixer quite as well because it's got these sharp edges that creates friction and therefore it doesn't move. So we have all these different things. I really liked your comment there on concentration, because that's a really big one as well. I have this additive potentially that's only in it so much of an amount, and that's the amount for that animal. And the person doing the nutritionist said that that's enough. But when I look at my mixer size and I look at the meal size of the animal and I look at the number of particles per gram or whatever of that particular additive, there might not be, in some cases, enough particles to fully distribute throughout the mix to where every animal, I'm feeding a day-old chick, it's only going to eat so many grams of feed. And so if I have a 5-ton mixer, I need enough particles to distribute out through that 5-ton mixer that every 5 to 10 gram sample of feed has that ingredient in it. That's very difficult when we think about it. And we're trying to do this, like you said, in minutes, in 2 or 3 minutes. And so all of those conversations about, what particle size do you want? What is the particle size? What is the distribution of this particular additive or ingredient that we're putting in? What type of mixer are we using? All make such a big thing. So from your perspective, knowing all of that and knowing that this is where one of the things I like to talk about here, and we've talked about on the podcast and with students, is we still talk a lot about the art of what we do in making feed. And I very strongly believe in the art, but I also will say one of the reasons it's an art is because we just haven't learned how to collect all the data and learn everything about it. And we probably never will. But with all of those things in mind, what kind of things do we need to do to prevent those segregation of particles during mixing, to get that uniform mix?
And you mentioned yourself different particles, different geometry, size, shape, and so on. Also, why, I'm always asking my students, why do you think that we don't use sand from Sahara in order to build something? Because they're too round. They don't want to interlock.
There you go.
They would love to stay, but they cannot. They just roll. So there are cohesive particles and there are non-cohesive particles. There is one research, I think it's from 2018 or something like that, Halidan et al. So they have actually published a very actually good paper where they described how impeller speed and mixing time could be influencing cohesive and non-cohesive particles. And they are saying that if you have cohesive particles, you will have to have a high speed rate of impellers. If you have impeller speed of 100 RPMs or something like that, then both cohesive and non-cohesive particles will have a sweet spot in a way.
Interesting.
If you don't have like non-cohesive, for example, particles, they don't like to stick together. They just would like to be separate from each other. And this is very typical. This could be a gravel or a sand from Sahara. And those particles are considered or defined as a free-flowing particles. They don't form any kind of clamps. They don't create a problem. They are easily poured and so on. But the thing is that they could segregate.
Hmm.
And in order to because in a feed mixture we do have cohesive and non-cohesive particles, and especially when we are talking about micro components, minerals and so. From the other side, there are cohesive particles, and you don't want them to be agglomerated all the time.
Right.
They stick together because of these van der Waals forces, maybe hydrogen bonding, electrostatic also forces, and they could agglomerate, and they could if they agglomerate, then you can't really say that your mixing equipment is bad. You just didn't find the sweet spot, basically.
It's time for our famous three. Evonik Animal Nutrition is committed to ensure food security and safety while reducing the ecological footprint of animal farming. Its products and services use evidence-based solutions that seek to promote animal welfare and reduce reliance on natural resources. All this is underpinned by long-standing industry partnerships and deep customer understanding. Evonik's focus on efficiency, sustainable, healthy nutrition, and collaborations with livestock farming partners creates value for customers and consumers.
Sure. Yeah. So I think too, I think as part of all that discussion, I want to get in our last few minutes here talking about some of the mixing equipment side. Generally speaking, the mixer's job is to randomize particles and create a uniform mix. And if we have all of the ingredients properly sourced, properly chosen, right contributions and concentrations and all of those things, the idea of something like unmixing doesn't make much sense because the mixer's constantly trying to make it more and more mixed. But then at the same time, if we do have some particles that have just very significant changes in density where they're going to sink or they're going to float on top of the mixer, or like you said, they're cohesive or non-cohesive, then at those times, if we don't have our mixer properly filled or we don't have it properly maintained, while a mixer that is being used properly shouldn't unmix anything. People talk about, well, what if you ran it for an hour? Could you unmix things? Generally, no, if the mixer is properly filled and properly maintained and you have the right ingredients. But if any of those things are wrong, there is the potential for maybe things to float to the top and not be brought back in. So with that idea, a lot of what we see now in many new situations are these twin shaft ribbon or paddle or combination type mixers going in together. And I know you guys have also developed a new technology, and I'd love for you to share some about that as well. So can we talk just a little bit here at the end about what are these different mixer designs, what works well in what situation, and what led you guys to looking at your own kind of a design for mixing there?
Yeah, so basically, we considered until 2018 when we started doing this project, ISDECA project. So we were actually at the Center for Feed Technology a little bit of, we had twin shaft paddle mixers, and we really believe that twin shaft paddle mixer is a very good piece of equipment that is spread now everywhere, from car brakes powder to pharmaceuticals to, of course, feed and food and so on. And the problem that we have faced many times, especially within this research area, you have to be quite precise. So we wanted to understand how do we add some novel ingredients that are actually coming as wet ingredients like ensilage, protein-rich ingredients which are having 50% of water and they are extremely viscose. So we have seen many times that performance of a twin shaft paddle mixer wasn't really the best one. And we had this lumping. And, if you have like a lump, you break the lump and you see that the outside is wet and inside is dry. that basically means that you haven't performed what you actually originally wanted to perform. So a colleague of mine, Mr. Nicky, he was on Monday, because we're having Mondays meetings, and we were just discussing about how difficult was to do the mixing process of these wet ingredients. So we had just like a few drawings at the whiteboard, and we thought like, okay, I think it's worthwhile trying. We approached to another colleague, Dr. Carlos Salas Bringas, and we discussed about how to create a mathematical model of new thing that we were just thinking to create. So after 2 years, we already had 4 master degrees done with very nice mathematical models, and we created a very cheap 3D printed model with many different colors. It was almost like United Colors of Benetton, like all the plastic, different plastic that we had, and we tested it. So we have seen that coefficient of variation was honestly, with such a plastic device, strangely low. Then we thought like, oh wow, okay, let me repeat. So we repeated. We had to respect scientific method. So we have seen that this is repeated. Then what we did some statistics, wrote a report, approached to our technology transfer office, and they were interested to sponsor further our research. So in 2019, we ended up with 60 liters lab scale mixer. We presented this to further on to Norwegian feed industry. They were very interested in that, and then we got some money from the state in order to create to upscale the process. And for this upscaling, we also used a company, Simula. This is a Norwegian, the Norwegian simulation company. So if you want to simulate whatsoever you want, they will do it for you. So they sharpen it up, this mathematical model and of course physical model, and they have told us that we definitely can upscale this one in many thousands of liters. So once we had 1,000-liter mixer, and we have seen that everything is actually performing in the same way, like in 60 liters mixer, then we definitely knew this is something that we can definitely patent, and our technology transfer office patented this. So we can say that this DECA mixing now, it's a patented technology which is beneficial for the aquaculture industry, and especially in Norway's salmon farming sector,
Right, sure.
which definitely aims to increase production fivefold by 2050. So this is DECA technology allows the incorporation of sustainable marine ingredients by of course reducing dependence on imported soy protein and fish meal, for example. So you can relatively use cheap raw material, which is actually just here behind the corner, and you can, those are byproducts, of course. Like, for example, I'll just give you an example. There is a pea starch, because there is a company that is producing, their original idea is to separate starch from a protein, and they are selling pea protein. That's the main business. But they have lots of pea starch. Or maybe if you want to have milled oat, that's relatively cheap. So now you want to have a new ingredients, and you put in this starch or this milled oat, you put hydrolyzed fish meat, bone meal, and so on, and then you mix it together to create a high protein ingredient. You can't mix them if you don't have a good mixer. So you have to have a mixer that constantly sprays and deagglomerates, and deagglomerates within the entire kind of a structure. So we tried this ISDECA mixing technology, and we have seen that we are actually having high homogeneity. It's very efficient if you want to have dry powder and you want to mix it. Then we know that we are getting to this European standard, which is 4.5 or less coefficient of variation. And we, with this ISDECA technology, went so low that it could be considered as a machinery that could perform quite well even for medical purposes or pharmaceutical purposes with the coefficient of variation under 2%. But then when we talk about liquid addition, we have, and I have to say, I have to admit this one. I have made a mistake by calculating. I was preparing to perform the experiment, so it was the end of the day, and we were tired and so on. And I calculated wrongly to add 30% of a liquid. So I added actually 60% of a liquid. So when I took out a sample and I squeezed it, it was like a snowball. Very easy to squeeze it to make a snowball. But then there was an oil leaking from my hand. I was like, "What is this? This is strange. 30% shouldn't behave like this." But then I recalculated. I was like, "Oh my God, this is 60% added oil.
Yeah.
This is too much." Still, when we were running it through screw conveyor, it went perfectly without even flaking. That was, I have to say, a little bit shocking. Okay, this is good. We have to say to everybody that this perform in such way. I have to say that even if you have extremely viscous ingredients, like molasses or honey, you can add it without even spraying, but just like by dripping. Why I'm saying that, we had a customer, and the customer brought something that is extremely thick, very thick. So I just thought, like, look, I don't think that we're gonna mix this one. I'm not sure, but we had never mixed such thing. And he said, like, why won't we just like dump it in and we see what happens? I was like, okay, well, it's your experiment, so let me do it. And after 120 seconds, everything was, instead of white, everything was perfectly brownish, because his liquid was actually liquid, semi-solid, was brown. And then we thought, like, okay, now we know additional thing. So thank you. We had to say thank you to our customer that opened our eye. So we have seen that by comparing, of course, we run an experiment and we compare twin shaft paddle mixer and this is DECA mixer. And we have seen that eventually ISDECA mixer and twin shaft paddle mixer will come to the same point of a dry mixture. But twin shaft paddle mixer needed 190 seconds, whereas ISDECA mixer needed about 100 seconds in order to get to a coefficient of variation, which was under 4.5. And what also I have to say, which is kind of a maybe very important part, ISDECA mixer has 30% less material in order to build it up. So it's about 30% cheaper than twin shaft paddle mixer, and it has less impellers, less pedals, and it's a scalable process, as in the same way as twin shaft paddle mixer. So those are things that I can say in regards to this ISDECA mixer. Yes.
Well, I appreciate all the detail. So for everybody that's listening, ISDECA is ISDECA. So ISDECA, capital I, capital D, capital C in there. If folks wanted to learn a little bit more about the mixer, go look up, kind of see technically how it works, where would be a good spot for them to do that?
Of course, we are having it here at Center for Feed Technology. We have both 1,000 liters and we have 60 liter. Now our 3D printed model is in our own small museum, so that's not in the function. But also, this is now commercialized. So there is a feed tech company. This is a Turkish company based in Izmir. They are also producers of this equipment.
Okay, excellent. Excellent. Well, I certainly appreciate our conversation today. I think kind of the takeaways that are probably useful for people are there's a lot that goes into whether or not things mix well, from particle size, shape, density, the concentrations of things that are going in, like additives. All of that is really, really important and needs to be considered by the nutritionist and by the feed technologist. And that, though we've been mixing for, you said 40,000 years, that even still today, we are still working on developing new feed mixing technologies and new powder and bulk solid mixing technologies. So there are still ways to improve upon what we do, both in the understanding of what's going into the mixer and then how the mixer functions, and then potentially even on the equipment side.
Absolutely, definitely. When we are talking about mixing as we never think of mixing as something like state-of-art technology, basically. And when twin shaft pedal mixer was or has established itself as the technology for feed manufacturing, we stopped thinking that improvement is possible.
That's right.
So I'm happy actually that we came to this point, and I'm sure that the technology that we have developed could be even better.
Yeah. Absolutely. I agree. And that's good because that's job security and we keep working on it.
Yeah, exactly.
All right. Well, I appreciate our conversation. Again, my guest today has been Dr. Dejan Miladinovic. He is the head of the Feed Technology Center at the Norwegian University of Life Sciences. Dejan, thank you very much for the time.
Thank you very much for inviting me.
Once again, on behalf of Wise Genetics, I'm Adam Farnolls from North Carolina State University and the Feed Technology Animal Food Manufacturing programs here. I appreciate you listening to us. Thanks for joining the podcast. Thanks for watching on YouTube. Please like, subscribe. If you have any comments and things you'd like to see us talk about in the future, please do let us know. And otherwise, we will talk to you the next time.